times. So thank you for staying that late. Appreciate it. Okay, so I'm Eran, and I'm going to describe today the methods we developed in Trax to detect objects in extremely crowded images. So object detection in computer vision is the task of finding all the objects in the image, finding the locations and their types. So when we have a picture of cars, you need to find the bounding box location around each one of the cars, and so is the case with any other object that you have. In the detection stage, there might be localization errors. For example, this yellow box in here was detected as a horse, even though most of it is just the background next to the horse. So this is a false detection example. To the right, you can see example of pedestrian detector, which has some correct detections around the people and some false detections around the tree. And classical detectors usually had a lot of false detections like that. Modern detectors tend to be more accurate. And today there are modern detectors that are based on deep learning approaches, and they provide very nice results, but they are usually trained and tested with the most popular data sets used for academy. COCO and ImageNet are some of the data sets of natural images, which are used, and they are fine, but they are relatively simple in terms of the number of objects that appear in each image, as well as how crowded the object may get, how complex the structure of the image can be, and how many classes there are. So even if we have a detector which works perfect on images of this nature, it might not work accurately enough in more complex scenarios. For instance, these data sets of parking lots, the goal here is to count the number of cars and to localize each one of the individual cars. Since the cars are very crowded, it is more challenging for the detector to realize how it should split the detection in order to have exactly one detection per car or per object. These issues get even more complicated in the retail domain, which is the major domain we research in Trax. So in Trax, we perform object recognition in retail images. These are images that are taken in supermarkets, grocery stores, etc. They capture displays of shelves with products for sale. The objects here are the products, and the goal is to detect each one of the products. So we need to provide a single bounding box detection for each one of the products, like those green boxes here, which are, by the way, the actual results of our detector. So what you can see here is that domain is extremely complicated, or it's very complex. There are hundreds of objects in each image. They are very crowded. There are complicated structures. There are tens of thousands of different product types or different classes. So it's more difficult to generalize. And also, there are many common cases when standard detectors tend to fail for objects for this domain. So let's review some examples of failure cases. So here, you can see examples of 4 detections of the specific class of a green can of brand V. And all 4 of them look more or less okay. They look like the real object. The first one is actually okay. The second one is a bit inaccurate because it is a different type of can. It has a different top and a different aspect ratio. It is considered a completely different class. It's also a matter of fine grained classification that we will talk about later. But in the detection stage, we actually got a bounding box which is slightly inaccurate, and the classification will also be inaccurate because it will classify the wrong type of can. The third example is a complete mistake because it just recognized the logo area of a bottle as a can. And so is the case with the fourth example when you have a picture of a can on a package. It is understandable why the detector may think that the picture of the can is an actual object, but it really is not. What we would like to have here is a detection around the entire package and then a classification of the type of the package, not the can. And these are very common things that happen in retail. Here are some other examples of mistakes that can happen. So here on the left, we have something that looks like 3 bottles, but really it is just one package. In the center, we have something that looks like 2 packages of cat food. This face of a cat usually appears on each one of the packages of this brand. But this is a very sophisticated design where each package is just half a face and they are placed next to one another. Maybe it's a gimmick for sale or something, I don't know, but it also happens sometimes and it makes additional challenges. Another very common thing is that most of the objects that we have are very crowded. They are continuous next to one another on the shelves or in stacks, stacked on top of one another. So there is usually an overlap region between various different objects. So here you can see something that looks like a Fanta logo, and you can think that that is probably some sort of a Fanta product. But it's really just the area between 2 different logos of 2 different products. And those are all very common examples. They're not cherry-picked or anything. This is what happens all the time in our domain. So the conclusion here is that we need to develop a detector which is much more accurate, more robust, and does not make those assumptions that are usually implicitly made in standard detectors of natural images. Mostly, we cannot assume that the detection is good just because it looks like an object. It doesn't mean that the box was localized well. So in this slide, you can see various examples of cases where similar features appear in different types of objects in different locations. For example, the logo, which may appear in different locations for different products of the same brand. Or in packages, sometimes there is a picture of the bottle or the can on the package. So these are some examples of mistakes of this type. There is also the opposite case where a group of adjacent products may look like one big product, and the intermediate case of the overlap regions between adjacent products, which may also look like products of their own. So we need to develop a more generic approach for detection. And to do that, we propose adding 2 novel algorithmic components to the detector. So let's briefly review how most modern deep learning detectors look like. So this is an example of a common, one of the popular architecture of a deep learning detector. Essentially, we have an image. There is a backbone architecture with a convolutional layer which extracts the deep visual features of the image, and eventually it learns 2 types of information. The regression head, or the bounding box head, learns to regress the coordinates of the bounding box. So it learns to extract various bounding box locations for potential regions of objects. The classification head learns to differentiate between regions that look like positive objects and regions that look like negative objects or negative backgrounds, actually. In the binary simple case, it simply means that we learn examples, for example, if we want to detect horses in images. So it learns positive examples of horses, regions of horses, and negative examples of regions of the background, the sky, the tree, the grass, the ground, and so on. And it is relatively simple to distinguish between horses and background. They are visually separable. However, in our domain, the difference between object and non-object is might be less separable. So here in the top row, you can see examples of correct localization around objects. These are the green boxes. And the green boxes in the bottom row are inaccurate localizations. Even though each column, the local box for each column look visually very similar. So it is more complicated to learn to separate the space of good localizations and bad localizations. So to resolve that, we propose adding an additional head to the neural network detector, which learns another metric to estimate the quality of each detection. In train time, we first look at the nearby ground truth bounding box. These are the red boxes. And we have them in train time. So for each detection, we compute the overlap rate between the detected box and the ground truth bounding box. So we compute it as the intersection of a union. This is the formula. And it gives us a number between 0 and 1 for each detector, for each detection box, that tells us how much each detection overlaps with the actual nearby product. So if we are close to 1, the detection is very good localized, and there are very poor localizations with very small scores, and there are also intermediate cases. So this is the additional information we want to learn here. So we add an additional head to the architecture. We use the standard 2 heads for bounding box regression, objectness classification, and we add the soft IU head, which we compute the intersection of union between the true box and the predicted box for each box, and we feed it as the ground truth value of our new head. Since the value is between 0 and 1, we give it a probabilistic interpretation, and we learn it with a binary cross entropy, where with soft labels. The IOU is the ground truth label of objectness, and the 1 minus IOU is the ground truth of non-object. This way, we learn 2 different scores for each detection. So as a result of that, this detector learns to evaluate 2 scores to measure the quality of each detection. The standard objectness score from the standard head tells us how much each detection looks like the object. The new score from the IOU head estimates how much the detection overlaps with the nearby object. So these are 2 different properties, 2 different ways to measure the quality of the localization from different aspects. We can combine them in order to get more information, more knowledge to estimate the quality of each detection. So this was the first component we implemented. Next, we have the inference stage. After we have trained this network, we go to test and we feed a new image, and we get a set of many overlapping detections. This is the standard case with most detectors, at least. And the goal here is to eventually extract 1 box per each object. So we need to resolve the duplicates. In natural images, like this picture of a cat and a dog, it is relatively simple. But in our images, in crowded images, it is much more complex. The most common technique to resolve duplicates is non-maximal suppression, or NMS. It simply means that for each group of overlapping detections, we select the one that got the best score, and we drop all the rest. There are other alternatives that make some sort of averaging or other techniques to combine the boxes, but essentially they are all simple heuristics to combine the duplicates, and they work well. They usually work well on simple images, but when applied on crowded images, they tend to have a lot of mistakes. So when we apply them on a group of objects that are next to one another, and there are many overlapping detections that we don't even know which objects they belong to, if any. So when we apply naive approaches such as non-maximal suppression, we usually get mistakes. Some objects may be merged, or they may skip some of the objects. And also in retail, NMS may select the incorrect localization because it sometimes gets the best score. As we said, sometimes we may get a very good score for the logo area of a bottle because it looks like a can. So the bottom line here is that we cannot rely on those naive heuristics. And as an alternative, we developed a much more robust algorithm to resolve duplicates. So here's an example of how the space of all positive detection look like in a crowded image. This is an image of a parking lot with cars. So you can see that it's not very easy to separate if you don't have the colors. And so the algorithm we propose is as follows. We first convert each box into a 2D Gaussian. The center of the box is the center of the Gaussian. The dimensions of the box, the width and the height, correlate to the dimensions of the Gaussian, which are the sigma x and sigma y. In addition, each box has a score from the neural network. So this score correlates to a weight we assign for each one of the Gaussians. So we have a set of many Gaussians with weight. We make a linear combination of all of them. We normalize, and then we get a mixture of Gaussians. So this is a probability distribution of a mixture of Gaussians. Next, we apply expectation maximization in order to convert this mixture of many overlapping Gaussians into a mixture of few distinct Gaussians. Then are later translated to our final results. So to understand what we do in the algorithm, let's see the following image. So here you can visualize the input mixture of Gaussian and the output mixture of Gaussian. We described how we create the input mixture of Gaussians from the original overlapping detections. And this is visualized here as the heat map. The heat map in the background is an aggregation of hundreds of overlapping Gaussians. The green ellipsoids visualize the result, the mixture of a few distinct Gaussians. And as you can see, they actually, if they are converged properly, they actually resolve all the duplicates because each green ellipsoid is localized around an individual object. So we just need to convert it back to a box and we get our final results. So intuitively, what this algorithm does is it simplifies the original mixture of many Gaussians into a mixture of few distinct Gaussians while preserving the same structure of the entire distribution. Formally, it is applied with expectation maximization, which is done iteratively. The expectation step minimizes the Hale distance between the mixture of original Gaussians and the mixture of new Gaussians, and the maximization step estimates the parameters of the mixture of new Gaussians. There are many implementation details here that you can see in the paper and the code. So this is just the outline of the algorithm. The idea is that we use expectation maximization and a Gaussian parameterization in order to convert the original detections with all the overlaps into the set of distinct detections that presumably present one box per object. And that is the final result of the detector stage. We now need to estimate this entire algorithm. So for that purpose, we also published a new data set from images of Trax. Okay, you don't see the background. It was supposed to be here. Maybe it will load. I think it's stuck. Maybe it's too heavy. There was supposed to be here example of images from the data set. Also, the alignment is also in. I can see the images here, so if you want to, you can later see it here, or you can see it on the website. But there are images of very complex, like the images we saw at the beginning, hundreds of objects in each image. They're very crowded, tens of thousands of different classes, and all the other complex issues that we discussed. And we published, you can see this case is supposed to be the same line as well. This is the website of the project where you can find the code and the data and additional information. So the data is, so I can't really show it here because this talk, I can go from to the next slide. Yeah, okay. I mean, I don't have any animations, I think. So, and I had some animations. Oh. Okay. Now, just shows one slide. Okay, so let's continue from here.
You can move it from
המצגת, זה לא מצא המצגת?
Okay.
It's still the presentation, but now it works. For some,
Okay.
It doesn't work. Okay, it works for the results. So
yeah, you can use this follow, I think.
now it still doesn't work for the previous.
Okay.
Okay. These were supposed to be images here. Okay, let's continue here. So bottom line, we ran the experiments on our full methods, ablation tests, baseline detectors. We got much better results. Here there are some qualitative examples of results. In the green boxes, you can see how our method managed to correctly detect boxes even in very complex settings. We also attained state-of-the-art results on the 2 datasets of parking lots. And in general, we showed that our method can be used in order to accurately detect objects in various crowded domains. And this is the paper we published in the latest CVPR. You can see, you can see the images, I guess, in the webpage. Hopefully the rest of the presentation is okay. So the next step is to classify each one of the products. And it is also very challenging because we have so many different types of objects, type of products, and many products look very similar to one another. So the dataset is extremely fine-grained. For instance, each one of the Coca-Cola cans in here belongs to a different class, even though the differences are very subtle. Sometimes the difference is just the aspect ratio, a small variation in the logo. Sometimes there is I guess you can't even see it in the slide, but sometimes there are very small variations of the background pattern of the red part. Sometimes there is a stripe in here or on the top. Now consider the fact that we get images of displays taken from a far distance. So each individual product is a very low resolution. And sometimes it is, and often it is actually virtually impossible to distinguish between classes based on the visual appearance alone. So it is essential, it is very important to add additional contextual information in order to classify the products. So we published another paper where we, you can see the title of the paper, published in CVIU Journal, where you can see a method we developed to classify each product based on both its appearance and its context. I'm going to briefly go over the full method. So the idea is that instead of classifying each one of the products individually, we first model structures, in our case a shelf or a sequence, and we learn the entire structure. So we assume the structure of the shelf is a linear chain conditional random field, or a CRF, which is a type of a graphical model which makes some conditional independence assumptions. And using these assumptions, we can write the joint distribution of all the labels in the structure, given all the pictures in the structures, as a multiplication of factors. And then in inference, we use dynamic programming techniques such as Viterbi or forward backward algorithm to extract the marginal distribution of each one of the classes from the joint distribution. So in other words, we can classify each product based on the entire structure distribution, which gives us both visual and contextual information. So the parameterization of these potentials are log linear. This is the unary part, which is equivalent to logistic regression. It learns the same, the visual features are learned by a CNN. This is standard. The new part is the pairwise potential function, which has this new parameter matrix of which captures contextual information. The P is the transition matrix. Each element, Pij in the matrix, represents the transition from class I on the left side to its neighbor on the shelf, the class of class J. Now this class is huge, because if we have 1,000 classes, then we have 1 million transitions. And also it is very sparse, because most of the transitions don't really occur. There is relatively a small set of transitions which actually occur and have the information we wish to learn. So if we learn the parameters of P directly, it will probably not work very well. It actually did work very well. We have the full experiments in the paper, but even without performing the experiments, you can guess that it would not work well because there are too many parameters and too little examples. So the solution for that case is to factorize the P matrix into two lower rank factors. Similar to the works done in language processing, where you learn word-to-vec embeddings. In our case, we learn embedding. The rows of the factor matrix represent an embedding space which learns to capture the contextual semantic information of the classes. So here you can see examples. The leftmost row, the left column are various examples of classes. And next to each class, you have the 5 nearest neighbors in the embedding space that we learned. The similarity measured here is not a visual similarity that is measured through the CNN, but rather contextual similarity. So it's the equivalent of words that have the same meaning in a sentence, and they are embedding in close proximity. In our case, products that have the same meaning in a shelf are products that usually belong to the same archetype, and they tend to appear in the same context, maybe in the same display. So they are interchangeable in the contextual information. So this is the additional type of contextual information that we can extract using this parameterization of the CRF model. The problem here that before we managed to actually converge into that space of embeddings, we had to optimize the log likelihood of the CRF function. And once we factorize this P matrix into two matrices that need to be learned, we got a highly nonlinear sequential function, which is tricky to optimize. And it actually does not optimize well when you try to optimize it directly. And eventually we managed to find a solution to optimize it. And for that purpose, we developed the following architecture, which is based on pairwise samples of two neighboring objects and two streams of a neural network. The top stream takes the visual image of the product to the right and learns the visual features of the CNN, where the bottom stream takes the neighboring class to the left and learns its embedding vector from the matrix R, the factor matrix. Now, the entire parameter set of this architecture is equivalent to the parameters of the CRF. So we actually use this architecture as a surrogate likelihood in order to learn the parameters of the full CRF, which models the full shelf. And in inference, we take this parameter and apply standard inference for the entire sequence. The major advantage of this architecture is that it allows us to integrate batch normalization in an efficient way, which gave us the added value we needed in order to actually optimize and converge into a good solution. So when we used this full method, we managed to get much better results for classification, for objects, for product types on shelves, and also for letter classification in handwritten words. And you can see more detail in the paper. I just uploaded it to arXiv as well, if you want to see. So let's recap. We presented a new detection, a new detection dataset, which takes the detection challenge into new territories. We showed our soft IU layer, which learns the overlap rate of the boxes. We presented our EM merger, which resolved duplicate detections in a very robust and accurate way, and our method to classify each object based on both its visual information and contextual information that is learned simultaneously, and with our parameterization of a CRF with class embedding. So before we finish, I just want to announce that we are going to have a retail workshop in the upcoming CVPR in Seattle in June. This is going to be the first workshop exclusively dedicated to computer vision challenges in the retail domain. It is organized by some of the top researchers in the academy and some of the top companies in the industry. Our goal is to create a community to share knowledge, collaborate. So we will soon update the webpage of the project with more information, new dataset, challenges, competitions, call for papers, keynote speakers. So we are invited to visit, participate, attend, hopefully learn new things and share your knowledge as well. Thank you very much.